Hi, everybody. Welcome back to Dave's Math channel. This is a new feature I'm running now on daily math problems. These are math problems I try to post every day. I'm not able to do them quite every day, maybe every other day, but I post these on my a Facebook group that I use a lot called Classical Mathematics. I don't know if I'm allowed to advertise that here, but anyway, today I'm going to talk about a problem I posted yesterday involving a hexagon. As you can see, it's an irregular hexagon. The problem is to find the area of the ellipse that is circumscribed around this hexagon. So anyway, let's begin. So first I have to give you a formal statement of this problem. And the hexagon shown, it doesn't matter exactly where it's oriented in the XY plane. I show this for simplicity, but the problem originally stated was that you're given a hexagon with all angles of 120 degrees, just like for a regular hexagon. But it has two opposite sides of length 2, and all the other four sides have length 1. So if you like, there's two special sides that have twice the length of all the other ones. And now what you want to do is you want to inscribe an ellipse around it, as shown in this figure. You can always orient the hexagon so that it's in the XY plane as shown, and then the ellipse would just look as shown here. So now we want to find the area of this ellipse, which is shown in blue. So anyway, how do we do this? Well, you may remember if you learned about ellipses in high school, that the general form of an ellipse that's centered at the origin and oriented in such a way that its major axis is along the x-axis and its minor axis is along the y-axis, as shown. In other words, as long as it's longer along the x axis than it is along the y-axis, then the equation of this ellipse has the form x over a quantity squared plus y over b quantity squared equals 1, where a is the length of the semi-major axis, in other words, half the length of the major axis, which in this case is 3/2 or 1.5. And we don't know b yet, so we have to find b before we can compute the area. And then when we're done, we can use the formula for the area of ellipse, which is just pi times a times b. But first we have to get b. So how do we do that? Well, we note that we have a point. We actually have several points we know on this ellipse, 6 of them, in fact. All 6 vertices of the hexagon are on this ellipse. And we can use one of those points. I didn't show this one in this diagram, but if we use the point on the x-axis on the right, that, you notice the coordinates of that point, the x-coordinate is 3/2, and the y-coordinate is 0, so that means that a is equal to 3/2. And for convenience, I divided this hexagon into 10 equilateral triangles, so you can better tell what the coordinates of these points are. And so these are all equilateral triangles of side length 1, and I think you can see that that a is 3/2 because you have to go half a side length to get from the origin to the lower right vertex of the this triangle that's pointing upward in the middle, and then you've got the triangle right next to it that's also upward, and that at its top vertex here, I think you can see that the x-coordinate of that point is 1, and the y-component is square root of 3 over 2, which is the height of this equilateral triangle. You may remember that the height of an equilateral triangle of side length 1, whose base is along the x-axis, is square root of 3 over 2. You can get that from trigonometry. Like square root of 3 over 2 is the sine of 60 degrees. So it's just a sine of 60 degrees. Since you also have a 30, 60, 90 right triangle, along in the first quadrant here. Anyway, that's what it is. So the coordinates of p are 1 comma square root of 3 over 2. And now all we have to do is we just have to plug in the coordinates of that point into the equation of this ellipse, which I've shown on top. And I do that here. And I apologize if if this is too small for you guys to read. I'm pretty sure it is if you're watching on your smartphone. Maybe I have to do bigger slides. But I'm just gonna read the steps here. So we're just substituting the known values of x and y for this point P. And we also know A. The only thing we don't know from this equation is B. So when we make all the substitutions and simplify, we get 1 equals 16 b squared plus 27 all over 36b squared. And we conclude from that that 16b squared plus 27 equals 36b squared because the left side is equal to 1. And then we do some more algebraic simplification to solve for b. I'm not going to go through the details here, but when you're done, you find that b is equal to 3 times the square root of 15 all over 10. So that's b. A little bit messy algebra here, but we did solve for b. And now we have both a and b. So the last step, and this is larger print here, the last step is just to solve for the area. And now we're just using the formula for the area of an ellipse, pi times a times b. And we already know a and b, like I said, we multiply them together. And finally, the answer we get is 9 pi times the square root of 15 all over 20. That's the area of this ellipse. And I didn't solve this numerically. Maybe I should have. But anyway, that's how you solve for the area of this ellipse. That's how you solve this problem. So anyway, thank you for watching. Long live math. And I'll see you guys next time. Bye.